Thank you for joining us today. This is Wilson Ho. We are going to talk about tune mask damper for railway Groundborne noise control. In this presentation, I will talk about Groundborne noise mitigation and retrofit solution. Then, talk about an unexpected breakthrough in the railway damper technology last year, such that the damper is strong enough to reduce low-frequency rail vibration and the associated Groundborne noise. Before the trial tests on the operation railway lines, laboratory tests were conducted. For vibration reduction of 9 dB is achieved. Site tests will be conducted in Hong Kong and outside Hong Kong. And finally, I will talk about the potential impact to the railway industry and the EIA process. We will start with the current practice of the Groundborne noise mitigation and retrofit solution. Groundborne noise retrofit solution. Here are two types of vibration isolation platform. Both are high resilient fastener and can be retrofit. The retrofit process includes removal of existing base plate. It is time consuming. Other vibration isolation platform. Here we have the low vibration track LVT on the left and the floating slab track on the right. The floating slab track provides significantly better isolation than the LVT but very expensive. Use of floating slab requires extra space in the tunnel and higher loading on the viaduct. By all means, they are not able to be retrofitted. As a short summary, Groundborne noise mitigation solutions. We can either replace the existing base plate with high resilient fastener, which is time consuming, or slow down the train speed, which increase the journey time and operation costs. Both retrofit solutions are not favorable. Now comes to the exciting part, the breakthrough in rail dampers. Our damper already has good performance back in 2017. For most cases, only half installation is already sufficient. For cost savings, smaller damper were developed with size around 1/3 of the original damper. With improvement in multiple areas, the 1/3 size smaller damper provides similar damping as the original damper. The damper in 2017 consists 5 oscillators. Each oscillator was independently tunable from 300 Hz to 1200 Hz. The damper in 2020 consists 6 oscillators in 3 pairs. Each pair is independently tunable from 35 Hz to 2000 Hz. The frequency range covers the Groundborne noise region, which is between 35 Hz to 100 Hz. In short, there is 4 main improvements. In-phase oscillator pair, which provides stronger damping force. Independent tunable frequency for vertical and lateral direction. Metal-to-metal mounting interface to allow full transmission of damping force. And modular design to allow flexible installation pattern. Here is some data for half damper installation we published in IWRN 2019. It shows that half installations of the previous damper design is already sufficient for most cases. For the original damper design in 2017, half damper is already sufficient to provide 7 dBA noise reduction. The noise reduction performance maintains for a long period, up to present moment, more than 2.5 years and 4 grinding cycles. In other projects, it shows that the corrugation growth was also suppressed by 40 to 70%, which was published in IWRN 2013. With the year 2020 damper design, it allows flexible installation pattern to suit whatever site needs according to the site situation. It could be quarter installation, half installation, single installation, double installation, or triple installation. The modular design allows a quick and rigid installation. It also maximizes the oscillation mass ratio. Here is a short preview of how well our 2020 dampers perform. With the damper installed at alternative space, we call half installation, we achieved 17.9 dB whale vibration reduction at the lateral vibrations and with 8 dB reduction at the vertical direction. Even at the empty space, due to the effect at the adjacent space, we achieve 13 dB wave vibration reduction at lateral direction and 7.2 dB reduction at the vertical direction. With the whale damper installed at every space, we achieve 21.5 reduction at the lateral direction and 11.3 dB reduction at the vertical direction. You may be interested on how much vibration reduction at the tunnel structure. At the tunnel structure, the vibration reduction is only 4 to 6 dBA at the tuning frequency, although the reduction in whale vibration is more than 10 dB. Please remember that this vibration reduction effect is achieved by a damper of around 1/3 size of the original damper. We believe with the damper tuned to the Groundborne noise frequency, more than 5 dB vibration reduction at the tunnel structure can be achieved if the damper are installed at 2 or 3 damper modules at each space. Let us compare to the 4 improvements in the damper design: in-phase oscillation pair, independent tunable, metal-to-metal mounting interface, modular design. They are all patented technology. We have tested 3 types of whale damper: Type 8 with independent oscillator, Type B and C with an in-phase oscillator. Type C is same as Type B, but heavier oscillator and higher damping in the resilient layers. At the tuning frequency, Type C was vibration reduction similar to Type B, but wider vibration reduction spectrum. All the oscillators are tuned to the identical frequency, but the slight difference in the rubber properties leads to a slight difference in the lateral frequency. In Type A, the independent oscillation pair, a periodic destructive interference cannot be avoided, as shown in the animation. Type B has rigidly connected oscillator to ensure in-phase oscillation, which avoid destructive interference. Type B provides damping force better than Type A by around 30 to 40%. With our damper design, the oscillation frequency can be independently tunable along the vertical and lateral directions. Now come to the most interesting part: laboratory test result. We have a 500 kg steel board sitting on top of a 6 meter long wheel to simulate the unsprung mass of the wheel. A shaker providing broadband excitation directly connected to the steel board, the P2 resonance would appear laterally. In this setup, the P2 resonance is 47 Hz. Here is some photo of the experimental setup without damper, with 2 dampers, with 6 dampers installed. Here is some photos of the test setup. The yellow circle indicates the location of accelerometer attached to the bottom of surface of the whale foot. Here is the previous result presented in the paper, with 2 damper modules at each space, tuned to cover frequency range from 40 Hz to 60 Hz. Around 5 dB reduction was achieved at the P2 resonance frequency in both the whale and the fore vibration. It is also noted that a vibration peak appears around 35 Hz. It is the fore structural resonance excited by the adjacent activity within the building. After we submit the paper, we conduct further tests with higher shaker force to minimize the influence of background fore vibration. The 35 Hz background fore vibrations allowed 10 to 12 dB below the P2 resonance peak. In addition, we conduct tests to study the oscillator effect. Gap fillers were used to short-circuit the oscillators in order to study the vibration level with the oscillator being turning on and turning off. In other words, allowing the oscillation or disable the oscillations. The backlight are the P2 resonance whale vibration at the whale and at the fore without damper installed. The light blue lines are the vibrations with 2 damper installed under the wheels but with the gap filler to disable the oscillator. The dark blue lines are the resultant vibrations after removing the gap fillers. We can see that the oscillators provide significant damping around 8 dB vibration reduction at both the whale and the fore at the tuned frequency. Here is the diagram for the test setup. With the vibration sensor under the whale and on the fore, test 1 is to establish a baseline for the untreated whale. Test 2, 3, and 4, and 5 are to investigate the effective length which the damper are able to suppress the P2 resonance within the effective length. In test 6, 6 sets of dampers are placed close to the wheel set. First, we have the backlight showing the P2 resonance around 47 Hz at both the whale and the fore. Then we install the damper Type A independent oscillator tuned at 47 Hz at space far away from the wheel set. The green line shows the vibration level with damper installed at 1 spacing away from the wheel. The reduction becomes significant at the P2 resonance. The blue line with damper installed in the middle spacing, showing an even better vibration reduction. With 6 damper installed within the effective length, more than 10 dB reduction was achieved at the tuning frequency. We conduct the same test for Type B in-phase oscillator. Similar to the previous testing, when it is far away from the source, the damper shows low effect. However, when the damper are installed within the effective length, it provides large reduction than Type A independent oscillator. With 6 damper installed within the effective length, the reduction is around 13 dB at the tuning frequency. When we consider the multiple peaks along the frequency spectrum, the vibration reduction is only 6.4 dB on the fore, even with the 6 damper installed. Then we tune the oscillator at frequency, covering the adjacent peak. In each spacing, we have 4 oscillator pairs, 2 of them tuned to 47 Hz, 1 tuned to 41 Hz, 1 tuned to 50 Hz. The vibration reduction at the adjacent peak is improved to 8.9 dB. Again, the same test, but this time we are using the Type C damper with a large oscillator. Similar to previous testing, when it is far away from the source, the damper shows low effect. However, when the damper are installed within the effective length, it provides broader reduction than the Type B oscillators. With 6 damper installed within the effective length, the reduction is around 14 dBA at the tuning frequency. Let's compare to the peak-to-peak reduction for Type C of damper. With the large mass ratios and higher loss factor, the reduction at the adjacent peak is further improved to 7 dB. Let's talk about the potential impact to the rail industry and the EIA process. Site tests will be conducted outside Hong Kong. Welcome to proposed site for trials and for verifications. Within 1 or 2 years, the following practice will be adopted. Groundborne noise retrofit solution for 5 to 8 dBA will be achievable. That means Groundborne noise target may be adjusted according to local campaigns. No need to slow down the train for Groundborne noise issue, because damper Groundborne noise reduction is better than half train speed. EIA safety factor on top of the worst case scenario can be reduced or removed, saving the construction costs by minimizing the floating slab track usage, saving the tunnel construction costs because of the smaller tunnel size without the floating slab track. The industry has been waiting for a solution for decades. We invite you to witness this breakthrough. Thank you very much.